Hello, and thank you for joining our session, Bypassing Next Generation Antiviruses for Fun and Profits. I'm Ishai, the head of deep learning at Deep Instinct, and with me would present Shai, a data scientist and security researcher in the Deep Instinct deep learning group. Our outline is as follows. We are going to implement an end-to-end adversarial attack that generates runnable PEs that evades next-generation antiviruses, which using static PE features. In order to maintain the malicious functionality, we'll split our adversarial example into two phases. First, we would assess the impact of different features for that would be used by the malware classifier, and then we'll do a feature-specific modification only on features that can be modified without harming the malicious business functionality. Finally, we will show and demonstrate that a modified PE can evade not just the target malware classifier, but also other malware classifiers using the property of transferability, which we will discuss further in the following slides. Our agenda would be as follows. First, we will discuss about the differences and similarities between bypassing next-generation antivirus and a traditional machine and traditional anti-malware software. Then we'll discuss a bit about adversarial learning and what does it mean in the context of static malware classifiers. We will talk about the unique challenges of adversarial learning in the cybersecurity domain. We will present our own adversarial attack based on explainability. We will talk about the two main challenges, the lack of knowledge of the attacker of the architecture and features, and the need to keep the malicious functionality intact. And finally, we will hand over to Shai to see a concrete example of bypassing a real-life commercial next-generation antivirus. So let's start by talking about the similarities and differences between bypassing next-generation antivirus and bypassing a traditional anti-malware product. First of all, we are using different techniques and tools. In traditional antivirus bypass, we are using disassembling, debugging, and packing. And in next generation antivirus bypass, we're using techniques, data science techniques such as explainability, building a surrogate model, and generating perturbation. The end result is the same, bypassing the defender software, whether it's next generation antivirus or regular anti-malware software, with as minimal effort to the attacker side. And the methodology of the tools are basically the same. Whether you're using disassembling or explainability algorithm, you want to see a basic non-interactive understanding of what happened, of the business logic of the defender software. Whether you're using debugging or surrogate model, meaning building a model to simulate the malware classifier, you are trying to perform a interactive analysis or interactive experiments of the software and trying to understand what would work in order to bypass it. And packing or generating perturbation are two techniques, each in its own domain, that allows you to bypass a malware classifier without harming the malicious business logic. So what is adversarial learning in the context of malware classifiers? So first of all, adversarial learning or adversarial attack can take place in one of two phases. It can take place either in the learning phase, in which there is training data being inserted into machine learning algorithm, and from this a model is being produced. So if you inject malicious or sometimes called poisoned data, and therefore the attack is sometimes called poisoning attack, into the machine learning algorithm, it will train on it and will create a poisoned model, which would underperform on samples that are similar to the injected samples. However, this form of attack, the poisoning attack, requires a lot of efforts from the attacker. And while it, for instance, access to the data pipeline of the training of the model, and while it is possible in e.g. Supply chain attacks, it's highly unlikely, and therefore we'll focus on the other phase, and the prediction phase attack, in which case, sometimes called evasion attacks, in which case the attacker doesn't change or modify the model in any way, but it modifies the malware that is being presented to the malware classifier by removing, modifying, or adding features, and this is sometimes called perturbation, in order to affect the way the model classified this specific sample. The basic idea behind this is that the malware classifier is being trained on a certain distribution, and therefore it has a different decision boundary than the optimal decision boundary, and the perturbation try to leverage this. Now, in the context of static malware classifiers, or static analysis malware classifiers, the basic premise is as follows. You cannot train a malware classifier that will take all the files into and turn it all into features. In most cases, the computers or the machine have only limited amount of GPU, of RAM, of CPU, and therefore you are picking only handful of selected feature, the most indicative feature. Now, because of this, those features are quote unquote circumstantial evidence. You cannot handle everything. And for instance, while you can take very impactful features such as import address table, you would not be able to use to build the entire call flow graph in order to see the interdependencies between different functions, because it takes too much memory. And therefore, because of those circumstantial, quote-unquote, circumstantial features, you can bypass them and modify them in a way that would not harm the malicious functionality of the malware. Let's talk a bit about the challenges of adversarial learning in the cybersecurity domain. Besides the regular challenges, we have two main challenges. One is the attacker lack of knowledge of the classifier. And this is because, unlike in the computer vision domain, when the architecture are public domain, in the cybersecurity domain, every next generation antivirus uses slightly different feature. There are much more features to be used, not just the pixel colors, also import address table entries, dynamic API calls, P structural metadata, etc. The second difference is the original malicious functionality must remain intact, and unlike in a picture, when you can modify every pixel without affecting, it's still a valid image. You cannot arbitrarily change a byte inside a PE while maintaining its functionality. It might cause access violation or illegal instruction exceptions. Let's talk a bit about our own end-to-end adversarial attack. First of all, the threat model. We are using, as mentioned, static analysis-based malware classifier. The adversary has no knowledge about the attacker, the defender classifier type, architecture, and training set. The adversary does know the prediction score given by the attack model, meaning it's a gray box attack. It doesn't know just the label, but also the confidence score. The adversary has limited knowledge about the input feature. He must have a non-empty subset of feature that he would be able to modify and would affect the malware classifier, and how he does gain this insight we'll show shortly. The adversary has access to a data set of benign and malicious samples, and this is in order to find the proper value to which to change the modified perturbed features. And the adversary has no access to the source code of a sample he wished to modify, and this is in order to make it the attack easier to use by a larger audience. Let's talk about the different challenges we specified before. First of all, the lack of knowledge of the attacked model. We can mitigate this attack by using explainability algorithm. Explainability algorithms is algorithm that get as input a classifier, either black box or white box, and does produce the list of most impactful feature for a specific sample. In our case, the malware example that we want to evade the malware classifier. In this example, we see it in the computer vision domain when you see a picture of a snake being classified as Gartner snake, and we see 3 different explainability algorithms, and all of them are showing, are highlighting the most impactful feature for this classification, and you see that it's always the snake head, which does make sense. Additionally, we can use the concept of adversarial example transferability, meaning if we create a modified malware, aka adversarial example, that evades a specific classifier A, it's more probable that it would also fool other type of classifiers. How we can leverage this ability? We can try to attack a classifier which we are more familiar with, feature, architecture, etc. In our case, we would take the Ember classifier, which use a static PE feature, such as PE header metadata and other features that are used by many commercial next-generation antiviruses. We can attack this specific classifier, and then we can leverage the same successful attack and use the same modified malware against our target classifier. And in this case, we can have a very fast bootstrap of how to find the feature we want to update. Shai will present another technique. We use the sliding window attack that would also help us to understand the target classifier in a black box manner. The second challenge is keeping the malicious functionality intact. And in order to do this, we split the adversarial example generation into 3 phases, which are being repeatedly used. First, we perform a data set analysis in order to understand the values of different feature we want to modify. For instance, import address table entries, section name, etc. Second, we are finding the impact of specific feature using either explainability algorithm or the sliding window, as Shai will demonstrate shortly. Then we use a feature-specific modification. Certain features can only be added, for instance, import address table. Other features can be modified using a trappoling into the entry points, etc. And we repeat those 2 phases iteratively. Those 4 phases of dataset analysis, existing feature, explainability, selecting and modifying a feature, and modify the subset would eventually bring us to an attack that evades and bypass the target classifier. And then we will use the transferability property to bypass even more next generation antivirus classifier. Now, to show a concrete use case of how we bypassed a commercial next generation antivirus, I'm handing over to Shai. Thank you very much.
Thank you, Shai. Hi, my name is Shai. I'll be presenting the second part of our presentation of bypassing a commercial NGAV. So we will start about discussing a little bit about the dataset analysis, which is a step that we conducted independently. And here we want to find some information that will help us change the classifier's verdict, and we do that with the tools of data science. And we assume that all classifiers and all vendors, they use similar data sets. We want to have a data set that we can investigate with a similar distribution to what the commercial antivirus, next generation antivirus uses. So it will reliably represent the distribution of the features also. And for this presentation, we analyzed mostly one feature, which is the imports that are used in the benign dataset and the malicious dataset. And we used the dataset that came from Ember, which is an academic dataset with roughly 1 million samples. And we analyzed the import table of the benign and malicious, and we applied simple statistics to extract how many imports and which imports appear in a benign population and malicious population. The imports themselves are not malicious, of course. They are simply API calls, and they depend on the context of usage. And we ended up with a list that can tell us which imports are mostly found in the binary population of the benign population and the malicious population, respectively. So this table lists the top 3 most prevalent benign imports and top 3 most prevalent malicious imports, which you can see that they have a negative score and a positive score for the more benign ones. So we will use that later in our attack, as we will show. And the next question is, how are we going to find which features are important for our classifier? So we don't have access to the classifier. We can only query for the score. We do assume that it's a PE classifier, and it has some inherent features that are due to the fact that it parses PE files. So we assume that it will use the PE header, various sections, the overlay of the file, the imports, etc. And in order to understand which features are more important and we should perturb, we use a surrogate model, and this is the model that released by Ember. And we also use the SHAP package that will allow us to question the surrogate model and ask for the specific sample which features are most influential for that classifier. Just note that we're not asking the target classifier, we're asking the surrogate classifier about the feature importance. And here we present a list of the top 15 features with the highest SHAP score. And let's try to make it simpler. And we will highlight with green features that are under a complete control. For example, section names, for example, the header conf timestamp. With the orange highlight, we highlight features that are we have some control over. For example, we cannot easily remove or change import names, import libraries, but we can add quite easily. For the purple highlight, we show features that are we have indirect control over. For example, if we change a character, this specific character distribution, we're also affecting other characters distribution. And for the red highlight, those are features that virtually impossible to change or extremely difficult to change. So this is our highlights. It's not mutually exclusive, and features can also change our groups. But for the general purpose of the demonstration, this is how we split the features. And we have some good candidates to start perturbing and changing. And we will see our next method of the sliding attack window. So in this method, we're trying to detect which parts of the PE are the most influential. And this time we're querying the target classifier and not the surrogate one. And we simply slide a window. We can either zero out the entire window or scramble strings if we find in the window, and we pass that new modified PE to the classifier. and ask him what is the prediction now, what is the score. So for this kind of attack, we don't need a PE to be functional in any sort of way. We're just interested to see which areas of the PE have the highest impact on the score. So why does it make sense? As Ishai explained in the first part of the presentation, a lot of classifiers use circumstantial evidence that they collect from the PE header, and it is very difficult to understand, for example, if a string is actually going to be resolved to an import later dynamically, or it has some other meaning. So all of this information is collected and calculated by the classifier to the final score. So by hiding this information, we can understand what the classifier sees as the most important part or most influential part of the file. This attack is not easily applied on the PE header, simply because if the classifier expects to parse a PE header, then it will fail to do so. And the findings of this attack are not always very useful. For example, if we discover that the code section has a very high impact on the score, it's not very easy and simple to change it. So here we will show the illustration of our sliding window attack or sliding window probing. So we start with the malicious file. And the malicious is, of course, composed of the PE header sections and an overlay. And we pass that to the classifier and we get our prediction, our score. And for this example, it's -1. And the blue rectangle illustrates the actual sliding window that we move along the way. And each time we either zero out or scramble the strings. For this specific example, we used a 32 kilobyte sliding window, and we only scrambled the strings that we found in the window, leaving all other data as is. And finally, what we want to do is examine why the differences in the score occurred. So let's start playing, and we will show now the output of the sliding window attack on the sample. So as you can see, all the scores are still very malicious, but we have one score that is a little bit bigger, but not by much. But we think that at this point, it's very important to look at the precision that the classifier has on the score. And we change from 10 to the -11 precision to 10 to the -3 precision. And even though it doesn't look like much, but due to the nonlinearity of the classifier, this is very important. And now we will try to understand what is the specific address. And as we can see, it corresponds to the import table of the file. And this was what we saw with the SHAP package. SHAP showed us that the import library and the import function are very high in the importance. So both techniques agree here, and we can move on to the actual attack. For the actual attack, we will attack several features of the PE file. Here we will explain a little bit about how we attack them. So the first one is the checksum, and the checksum has no impact on the functionality of the PE. And usually correcting the checksum to the correct value only improves the score. And it's only relevant for a driver or a critical DLL, which is out of the scope for us. Timestamp has no impact on the functionality, and although it's a D-word or 4 bytes value with a possible of 4 billion possibilities, we here chose to just pick up specific values where the timestamp reflect no longer than 15 years in the past. And for each year, we divided it into 12 parts. So we try to match each month of the year. And this results only in 180 values that we can simply check. and conclude that attack very quickly. For new sections, we can add new sections with specific characteristics as we choose, either to be a code section or data section. And we can also generate buffers with the desired entropies that we wish, be it high entropy or low entropy. This attack usually did not very much improve the score in our favor, and we actually did not use it as a standalone attack. Entry point trampoline. In this attack, we can either insert a trampoline in the original code section if we have enough slack space, or insert a new section that jumps to the original entry point of the file. And this is what we used. And for the rest of the code section, we simply pasted a different code section from a very benign file from the OS vendor. And we used our prologue and conditioned it with an always false condition to the very benign code section, and jumped to the original code section of the file. So essentially the functionality remains the same. And as you will probably notice, all the addresses, all the virtual addresses and RBAs will be incorrect in that sense, but it doesn't matter because it's very difficult for a classifier to actually understand this information from the code section, and it is usually not done, as you can see. You will see shortly. For the new imports, we had 4 methods of introducing new imports, and the imports are, of course, taken from the list that we generated before in the dataset analysis. And the first method is the very well trivial one, is just introducing a new import to the file, but this usually causes the files to break, in a sense, and not load because of missing dependencies. Also splitting new imports that for libraries that already imported by the PE file and dumping the rest as strings could also cause the file to not load because of different versions of libraries. Keep in mind that in the dataset analysis, we work on a large dataset to extract the imports, and we don't want to go into details of versions of DLLs and which function names exist in which DLLs. And the last 2 methods are simply dump the strings into the overlay or dump it in a new section that will be, of course, data section. Renaming sections, same method as the imports analysis can be applied here to understand which section names are mostly found in the benign files versus the malicious population, and simply choose the most prevalent benign names. We didn't use that for the attack, simply because the PE file already had the most benign section names that we can want. And additional features that for this time we found them not contributing too much, such as the linker version, mean major OS version, and several more that we found by looking at the tiny PE project, and we got very nice ideas from that. So our next slide will show the results of the attack, and we will talk about several steps. So we start from almost a perfect -1 score from our target classifier. And the first step that we do is insert 10K imports into the overlay and correcting the checksum. And as we discussed before, this changes the precision most significantly, but the score is still very, very malicious. It's a -0.99. And what we hope to achieve by this is to make a big impact on the precision. And we found that inserting imports one by one, be it import names or as strings, does not have a big impact on the score. So we work here with a large batch of 10K imports, and we achieve a significant change in terms of precision. For each step, we also corrected the timestamp and the checksum, so we will not discuss this every time. And the next important step is the trampoline. And here we inserted a new code section, as we described before, with a prologue to a very benign code section that we extracted. And in addition, we added the same 10K imports from the first step into the overlay. And we can see that for the trampoline, we achieved a 0.1 almost change in the score. And in addition, the 10K imports into the overlay achieved a total of 0.519, which is very impressive. And again, the functionality of the PE remains the same. There is actually nothing that we did to change the functionality of the PE. But we're still in the malicious threshold, so it's not enough. And the next step will take 20K imports and iterate over them with 1K batches, choosing batches that improve the score only. And as you can see, we had a big jump here of 1.28 in the score, and now the classifier says it's a 0.8, and it's actually very sure that this is a benign file. And in a sense, this concludes the attack. So we had 6 additional steps of imports that we added, which are illustrated in the graph, where the orange line is representing the classifier score, and the blue line that we want to keep. Each batch that we add, we wanted to improve the previous score, which is not necessarily the optimal approach, because we can have combinations that we haven't checked, which achieve higher changes in the score. But we try to keep it simple, and it worked. So there was no reason to check a lot of combinations. And the blue line describes how each batch affected the score. So you can see that there are some batches that reduce the score, and some batches that improve the score, and the last batch improved the score by a 0.8 in total, and it put us in the benign threshold. So this concludes the attack, and now we can try to see what other antiviruses in our NGAV think about the file. So we started with 57 out of 68 detections. And our NGAV is currently detecting the original sample, of course, with a score of nearly perfect -1. And after our modification, we concluded with 30 out of 71. And our NGAV is no longer detecting the sample, alongside with 2 additional next generation antiviruses. And this also shows the transferability of explainability that Ishai mentioned in the first part of the presentation. This concludes my part of the presentation, and Ishai will give the summary. Thank you very much.
Thank you, Shai. And now let's sum things up. First of all, next generation antivirus is not a silver bullet, and especially when it uses engineered feature which attacker can understand and can modify in a way that would not harm the malicious functionality of the malware. Second of all, explainability is a dual-edged sword. While it does help internally for debugging, etc., it also can serve the attacker in order to understand which feature is more impactful and modify and focus on them also. And finally, we had some practical insights. First, the fact that the order in which you made the perturbation makes a difference. And if you choose perturbation A after B or B after A, you sometimes get different results, which is interesting. The second thing is that while small perturbations seem to have a very insignificant effect, like you saw in Shai's example, eventually, because of the nonlinear nature of those classifiers, you would get a sudden drop in the classifier, and therefore you will get a big impact, and therefore keep on trying, and eventually you will succeed. This concludes our session, and we are now open for a question. Thank you very much.